Copernicus data space ecosystem. And then we will look at some case studies for sustainable urban management with the data sets that are available in Copernicus data space ecosystem, including Sentinel data, Copernicus land monitoring service data, Copernicus contributing mission data, and how these different categories fit together. I will show you how to apply custom scripts in CDSE, and also how to create data products that you can share to desktop software or to a web GIS. And finally, we will recap once more how to set your user account type and service level to access all the data that you're eligible to access as a city administration. And then we will have a Q&A session. So CDSE, Copernicus Data Space Ecosystem, is the official data gateway and cloud processing platform of the Sentinel satellites. If somebody else is sharing Sentinel data on the internet, and we have quite many providers from hyperscalers or local clouds, they are getting it from us. We are the data gateway. This is where Copernicus data is first released. And CDSE aims to change the paradigm from downloading the data and processing it locally to directly processing it in the cloud without moving the raw data to your system. So it is an integration of a code base, a cloud processing platform, and a data repository. So what this actually means in practice, well, the typical data processing pipeline always starts with a remote sensor, a satellite. The data is downlinked to the Earth and sent to a server. And then we have a processing task, for example, the selection of an individual image, the calculation of a spectral index, the production of an output. And then from this kind of processing, you want to infer some sort of quantitative information, like a graph or a histogram or some sort of numbers. And then you want to show all this on your screen. And the big game change that Copernicus Data Space Ecosystem wants to achieve is that all of the processing pipeline should happen in the public cloud. Now, let this sink in, because this means that your computer's capacity, your server's quality, your RAM, your graphics card is not really going to be a limitation anymore. This means that we are massively democratizing access to Earth observation data, because you can do the access, the processing, and even the visualization, the rendering in the public cloud. This is what we do. So Copernicus Data Space Ecosystem is mainly here to share data from the Sentinel satellites. And I will be mentioning different kinds of Sentinel satellites again and again, and we will try to recap again and again what they are useful for. But here I want to give you a brief overview. Our main workhorse is Sentinel-2. This is an optical satellite. So it takes pictures like a photo camera, but not just in the typical optical values of your regular smartphone camera of red, green, and blue, but also in spectral bands, parts of the optical spectrum, parts of light, which are not visible to the human eye. These are mainly in the near-infrared, the mid-infrared, and the shortwave infrared domain. And this allows us to see places which are hotter than their neighborhood. This allows us to infer vegetation conditions. And it has a revisit time from 5 to 3 days. So every 5 days, it's taking a picture. Sentinel-2, since it's an optical camera, is mainly limited by clouds. You don't see through clouds with Sentinel-2, but if there are no clouds, you get really, really high quality imagery. Sentinel-3 is a different satellite. It's actually mainly optimized for ocean sciences. It has a lower spatial resolution of 300 meters. It collects information in 21 bands, so it's actually splitting up the optical spectrum into far more details than Sentinel-2 or your typical RGB camera. And it has daily revisit. So every day it's generating a new image. The thermal imager has 1,000 meters spatial resolution, and the optical imager has 300 meters resolution. So it is possible also to find hot places or forest fires with Sentinel-3. And then we have Sentinel-5P, which is a very low resolution hyperspectral imager. This is a sensor focusing on air pollution. It maps the whole globe every day, depending on clouds. And it provides direct output to various air pollution or air polluting data product, air polluting substances in the air. So these three are our main optical satellites: Sentinel-2, Sentinel-3, Sentinel-5P. They take regular images like a camera. And then we have a radar satellite, Sentinel-1. Now, radar is also part of the electromagnetic spectrum, but it's different than light. Its wavelength is approximately 10 centimeters. So Sentinel-1 data will be recording interaction of radio waves with structures that have approximately this size. Now, all you need to know right now is that Sentinel-1 is not dependent on sunlight. It's not obstructed by clouds, so you can measure in the polar night, or you can take an image of your city also when it's completely cloudy. And it's possible to map vegetation, buildings, and also water surfaces using Sentinel-1. And then what we have what we call analysis-ready data. So for viewing a seamless image that's not obscured by clouds, or building a machine learning application where you have a machine ripping through thousands of images that you're not looking at with your native eye, we have mosaics of Sentinel-1 and Sentinel-2 data. So these are monthly or quarterly average images where the clouds and the noise are removed. And these are also available now for a long time frame, actually longer than marked here, from 2016 to 2025. And then you can look at long-term changes or use them as a baseline. And similarly, for Sentinel-3, we have marine and land products, which the land products relate to vegetation, the marine products to water quality. And a recent addition, actually since a year, Copernicus Land Monitoring Services data are also served in Copernicus Data Space Ecosystem. Now, these services are part of the Copernicus program, and their purpose is to deliver complete data products for evidence-based policy. So not just the images themselves, but actually results, the numbers, the maps that you can use in your decisions. This is a comprehensive service of environmental variables, also highly relevant, of course, for urban monitoring. And these are calibrated data sets. They are regularly checked and updated year by year, and their accuracy is very closely monitored. So we have land cover, we have soil moisture, we have snow cover and snow water equivalent, we have surface temperature, we have a lot of vegetation parameters for agriculture and also for urban vegetation health, of course. And we have lake extent and water quality. These are the main data sources in Copernicus Land Monitoring Service. And then additionally, we have Copernicus contributing missions. One of the most important points of criticism towards the Sentinel program is that the images are low resolution. We hear this every day. The images are 10-meter resolution. This is a result of a lot of development, and it makes a good compromise between spatial and spectral resolution. But for some applications, you need high resolution data. And so in the framework of the Copernicus Contributing Missions program, additional high-resolution images are being bought and supplied to specific stakeholders. And these data sets are higher spatial resolution than the Sentinels. They are typically 2 to 5 meter resolution, and there is a mosaic once every 4 or 5 years. The main users are actually the institutions generating the Copernicus services themselves, but public institutions are also eligible to view and download these data sets. More on that later. So far, what you have learned is that Copernicus Data Space Ecosystem is for processing data on the cloud, and that it's not just for raw data. So it's not just for sharing the images generated by the satellites, but we have a portfolio of data products ready for AI analysis or ready for quantitative studies of urban health properties or climate or vegetation, depending on your application. So you can explore these products. You can also develop your own on top of these services because the cloud is there for you. Now we want to dive into data access, and the magic word or the magic abbreviation here is API. API stands for Application Programming Interface. This means a language that enables your computer to communicate with the server. It enables you to run code on a remote server that's actually hosting the data. Now, why do we need this? We need this because data volumes are massively growing. You can't possibly store all the data you need on your local computer, but also cloud processing capabilities have grown. And so the whole approach of having a big server and storing all the data there is technically over. The data is stored in uncompressed, streaming-ready formats, which means that you can get only the little part of the data you need. You don't have to directly download a full data product or a mosaic tile. And actually, you can request the custom end product that you want, not just order from a selection of raw data sets. The pre-processing, the subsetting, the analysis, the visualization is done in the cloud. Let me give you an early example. If you have worked with GIS before, you're probably familiar with WMS, web map service. So here we have a large data set that's stored on a server. And the API, the Open Geospatial Consortium API, allows your computer to send a request to this data set. You don't need to download all of it, it tells the remote server which part of the screen is showing what part of the map, and the server prepares the map for you, and your software or your web GIS can work with it directly. This has been used for maybe even decades. It's an early example of API access to data. An analogy we like to use is the alien fast food gourmet restaurant. I mean, normally if you want food, you have to select between cooking something at home, which is what you specifically want, or going to a high-end restaurant where you get something very high quality, but you have to wait for it to be prepared, or to go to a fast food, a drive-through, sit down in your car, and then get the food there delivered to you in seconds. Now, API accesses sort of all of these three. There's no preset menu. You order exactly what you want. It's prepared instantly right on the spot. It's packaged the way you want it, and it's very fast. There's no waiting time. So a catalog API allows you to access the list of data sets that fulfill certain criteria and that are available on the cloud. You choose a data set, you set a quality filter, you set the output format, you forward your credentials, and the API gives you a list of available images. But we can also have very complex APIs that actually enable full processing chains to be sent to the server. So you outline a processing code, a sequence of analysis steps, and this is not running on your computer. It's sent to the server, and the server does it for you on the cloud, and then the end result, the map, is sent to you, or it's pushed to a web GIS. This is what our APIs can do, for example, OpenEO, right? So the advantage of API access is that the data is instantly there. It's what you need. You're not storing raw data. You're not processing the raw data on your machine, and it's very fast to upscale. So on the investment side, API access is worth it because you don't have to first buy a big infrastructure, estimating the size of your demand. You can start small. You're running everything on the cloud. And then as your service grows, you can just grow the processing demand, your virtual machine on the cloud. Again, you can do this in a completely dynamic way. And this also means if you are looking to build a GIS system for your city, you don't have to create a public procurement for the data infrastructure, the data storage, the data handling. It's done. It's already there, publicly available by the commission, and you can use it as a public service. So how can you access data? We have several different APIs, and they do different things. They have different capabilities. The main ones are OData, S3, Stack, OpenEO, and Sentinel Hub. Sentinel Hub includes Copernicus Browser, which is what we are going to use to look at satellite imagery in a couple of minutes. OData and S3 are mainly for data cataloging and downloading. You can send a filter, you can select the data, and it's sent to you very quickly. But this is only for raw data. If you want to download the imagery, if you want to have a full time series of your city on your server, you probably want to go through OData or S3. Stack is a bit different. It's a catalog service, so it allows you to understand what's on the server. You can do a certain level of processing on the streamed files, so you can, for example, calculate the spectral index or basic band math. And Stack is also integrated into desktop software such as QGIS. So this is a higher level of data access. Now, OpenEO is designed for interoperability. It's an open source solution. It even interacts with multiple backends at the same time, and it allows you to do very advanced analysis in the cloud. This includes user-generated processes, physical models, deep learning, and it's also integrated nicely with QGIS. This is coming soon. And Sentinel Hub can do data downloading, but it can also do cloud processing and statistics for individual images or for bulk large data sets. It can do spatial statistics, time series, spectral indices, and the outputs can be sent to OGC or to QGIS or visualized directly on your desktop in a browser. So these are the tools you can use to access data from the server. And we are going to go in this webinar through the Sentinel Hub API and through Copernicus Browser. Okay, now for our little hands-on, we are going to explore how to view satellite data in Copernicus Data Space Ecosystem. The first thing you need to do, if you haven't done it yet, is to register on Copernicus Data Space Ecosystem. You can do it on your phone using this little QR code, or you can go to this registration page that I am showing here in the presentation. This is going to give you the exact guidelines on how to register. It's a fast process because this is a public service, so we are not storing much of your data. We are only doing we are only storing your name for reasons of following the quota. We're not tracking your use. We're not saving the code you generate. You retain all the ownership to everything you are doing on Copernicus Data Space ecosystem. So once you have registered, if you're a new user, you will see this green button. Then you will fill in your details. You'll get a verification email, and then that's it. So now we move to Copernicus Browser. It's browser.dataspace.copernicus.eu. Or from the main page, if you just click Explore Data, you will be taken straight to Copernicus Browser. So what do we see here? We see an image of Europe. It's apparently composed of satellite imagery, and we have this little notification, please zoom in or search for a location of interest. So I'm taking you close to my hometown. I'm Hungarian. I live just nearby Budapest. If I zoom into this place, or if I search it in this little search bar, it's going to take me to the place. And if I click the big green button, Show Latest Date, it's showing the latest Sentinel-2A image. It's the level 2 image, so which means there's some atmospheric processing done. So maybe you envy me a bit. We have wonderful snow right now in Budapest. This is a clear sky image. Note that it's not from today. If I click on the calendar panel, I see that it's the latest cloud-free image. There was also one from the 21st, but that image was cloudy. So by default settings, I can set the cloud threshold, and then it's giving me the image from the 18th. Right? I can zoom in. I can pan around. I can select imagery from a different date. So let's see a summer image. I can go back to July 2025. And now you see that the city is all green, of course. Here in this panel, I can set the background image, OSM, OpenStreetMap, or the Sentinel-2 mosaic. I can add labels or remove them, and I can add or remove country borders. So here are some of the very basic tools. I've told you that Sentinel images are not just in the visible optical domain. Here is the little spectral explorer, which allows you to look at the exact values of the output bands. This is here blue, green, and red. And then this is all the near infrared. You can see that the intensities are a lot higher than for visible light because the atmosphere obscures less. And so we are also using these bands over here to take a closer look at what's going on the ground. One thing we can do is create a near infrared false color image. So here vegetation is red, because the near infrared band is assigned to the red channel of the image. And healthy vegetation is bright red, and sort of less healthy vegetation is a duller or darker red. You can also create a spectral index. So if you just click on Custom and Index, you can select individual bands. So you can take the red and the near infrared and create an index, and this is going to give you, no, the other way around, like this. Yes. This is going to give you the intensity of vegetation vigor. You can see I'm subtracting the red band from the near infrared band, and I'm dividing this by the sum of the two. And so I get high intensity in areas which are green, like this park, and I get low intensity in areas where there's no vegetation. You can also have a default visualization of this parameter, NDVI. We will be talking about it a lot. So here you see how green is your city. Now in Copernicus Browser, this is not just about looking at images, but you can actually generate some quantitative information as well. So if we go to this park, for example, I can draw a little outline. Like this. So this is my area of interest now. And if I click on the histogram tool, then it's showing me the distribution of NDVI, the distribution of vegetation greenness within this area. I can also create a time series over here. Now I am looking at the time series of vegetation greenness in this area. I can remove the cloudy images a bit. And now you see that greenness, of course, drops for the winter, and then it climbs back up in summer. So these are some of the very, very basic tools that you can use for exploring imagery in Copernicus data space ecosystem. Now, how does this actually relate to urban planning or urban management? Let me give you another example. Here we are going to Paris. You know that Paris is famous now for its advanced urban green space developments, among others. And this circular place here has been recently renovated from a parking space or a paved area to an urban park. I hope you're, I don't see the chat, but I hope that Alex is pasting the sharing links in the chat. If you can't follow me, then you can just click on the link and click on the next link, and Copernicus Browser will take you to the right place. But I can also give you the name. This is called Place de la Catalogne. In Paris. So if you type this in, it's going to take you to the place. And this is just an image from August 2025. Now I can go back in time and go all the way back to 2015. Let me check what this place looked like before. You can see that now it's completely gray, because before it was a paved area and now it's converted into an urban park. Now it's winter, so you don't see much of that. But again, if I create an area of interest, I can switch to NDVI, vegetation greenness, and then we can try and find the date when this park was created and how this is influencing the local urban green space. I can go back to 5 years, and this is the API at work, what you are seeing. So while our browser works, in the background, the Sentinel Hub Statistics API is taking all the images in the last 5 years, all the Sentinel-5 images. For this little area of interest, it's calculating the NDVI, and then it's giving us the value inside this time series. So what you see right now is that the NDVI was very close to 0 before August 2023. And then apparently the screening project started, and now it's all the way up to 0.6. So you can actually identify when the intervention happened and what the effect of this process was. And I can show you something else. If you want to share an image in a Copernicus browser with somebody, like to verify that this is an actual official satellite image, you can just click on share, you click generate, and then here you get a short URL. If you paste this into your browser, it's going to take that person or take you immediately to this image with this visualization on this date. So it's like possible to share images directly also with people who don't have a GIS tool or a strong computer. Right, so these were the very basics of accessing data with Copernicus Data Space Ecosystem. Let me just move forward to a case study. So now I'm going to walk you through individual tools for monitoring urban green space in a different town. This is going to be Riga, Latvia. Riga recently hosted a major remote sensing conference, and I had a chat with the city administration there, so I can show you some of the tools that they are using. This is a recent satellite image of Riga. The image is from the 31st of December. Nice snow, not much information on urban green space, right? So what do we do? Of course, we go to the calendar view and we can select an image from summer. I have selected one here for you. So this is from the 14th of August. And already you can, of course, discern the green areas from the built-up areas. I'm removing the labels for a while. So you can see the waterfront, you can see this network of parks, and you can also see that some areas of the city have more trees than others. Again, if you want to take a quantitative approach, then you can calculate NDVI, and you can even do a histogram for the whole city. So if I am just very quickly clicking around the perimeter of the inner city, I can calculate a histogram, and this is going to give me the distribution of various levels of urban green space, right? We have some areas of water. We have some areas with sort of low-level vegetation, and we have the parks and forests, which are distributed around the town. So this is a small set of tools for mapping urban green space. The problem with this is, of course, that it's easy to run into a satellite image which is cloudy. So especially in Riga, it's very rare that you get conditions like this where there's absolutely no clouds in the sky. And also, NDVI is, it also has its limitations. It's a relatively simple conversion from this spectral index to vegetation health. So you can use other tools as well. This is something I can show you here. This is a different approach to vegetation health. It's called KNDVI. And the way it works, if you open up this custom script option here, you're actually looking at the code that is running as part of the API request. So we are requesting band 4 and 8. We are requesting the cloudy layer. We are applying a small palette. And then we are doing this classification. And it's possible to directly edit this code, but it's also possible to take the code from a repository. And here in the custom script repository, I have a script called kernel NDVI. Here's the full text of it. The palette is the same, but the calculation is different. The mathematics are slightly more advanced behind it. So if I just copy this and I paste it in the script window over here, then I am applying a different calculation and a different visualization straight from the repository. Right, so the name of this repo is custom-scripts.sentinelhub.com. And you will see that it has a collection of scripts for many different applications, grouped by satellite. And you can take this simple copy and paste approach to using these scripts and applying them in Copernicus Browser. So what we have here is a small classification of the surface into water, bare areas, and green areas. And it's also possible, again, to calculate histograms or time series on this image. But in addition to using a different or a different spectral index, it's also possible to use a different data product. Right here, actually, instead of the individual images, we are using a Sentinel-2 mosaic. So I'm going back to the true color images just to allow you to see this. Here are some clouds, right? And if I change the data set over here from Sentinel-2 to Sentinel-2 mosaics, I am getting a big seamless data set with no clouds. All the clouds are removed. These are generated once every 3 months using all the cloud-free pixels. And so if somebody wants to map urban green space in this city, maybe they are better off actually using this mosaic instead of using the individual images, because then you are filtering away the clouds. This is the mosaic again. This data set here is a visualization based on the mosaic. Here I have applied another trick to the script, because I'm not just calculating the greenness, I am making all the pixels transparent which are not green. And the use of this is I can create a compare. I can make a scene where 2 images are one on top of each other, and then I can evaluate the results looking for different properties of the landscape. So if I click Add to Compare here, then it's going to show up in this compare view. I can go back to the normal visualizations. I go here in True Color Cloudless. Once more, I can show you this is the layer itself. I click Add to, and then Add to Compare. And then I move over to this compare mode. And now I have a slider, right? If I change the order of the data sets, yes, then you see that underneath my vegetation greenness image, I have the regular Sentinel-2 mosaic of the city, so I can see where I am. Now we have taken care of the cloud problem, right? We are using the mosaics, but this is still rather low resolution. Let's see what we can do with higher resolution imagery. This is where the Copernicus contributing missions data sets come in. So if you have filled in your user registration form, and you have clicked in the request for accessing Copernicus contributing missions, This is going to be reviewed by a person. They check who you actually are. So you might not get access to it right now, but you can go through the links later on again. So here under Copernicus contributing missions, I have the VHR mosaics from 2018. Maybe I can even show it. From 2021 and 2024. Obviously, the 2024 is the one with the highest quality and the most recent data. And again, on this kind of image, I can also apply the approach for high resolution mapping. I can apply a custom script, which colors everything green depending on the greenness level, and it leaves everything else transparent so that I can find my way through the city and I can actually evaluate the data. So what have we learned about urban green space mapping? We have learned true color images, we have learned mosaics, we have seen custom scripts, we've looked at Copernicus contributing mission mosaics, we have applied custom scripts to this as well. And so what you see is that there's various sources of data available with different resolutions. It's possible to create automatic quantitative processing. You can look at histograms and time series. Let's move on to a different domain here. I want to introduce you to flood mapping. This is done through Sentinel-1 synthetic aperture radar. As I said, these are not light, but electromagnetic waves. And the problem with this is that you can't visualize them in true color, but you can see a lot more because clouds are not obscuring anything. This is my little example here, the city of Ferrara. So you can somehow recognize parts of the city on this image. You see that agricultural areas are sort of orange or bluish, and the city is yellow because it produces very high reflectivity, and water surfaces are dark. This is the key thing you have to remember for urban flood mapping with Sentinel-1. Let me show you an example of this, again, directly in the browser. This is a place called Beira in Mozambique. I'm just showing this overview image because what you see here is a cyclone actually hitting the shore. So here's the shore, here is the sea, and the redness reflects represents the height of the waves. So this is actually the eye of the cyclone, and this is the windstorm hitting the shore. And this cyclone has caused massive floods in the area, and we will look at these floods in a comparison view again. So first of all, let me show you the city. Again, the sea is dark red or black. Flooded areas over land are black or deep blue. And this is the situation before the storm. And now I am adding to the comparison the image from the 20th of March. And you see that massive areas of the city are flooded. This here is sort of a dryland area north of the town. That's not a disaster in itself, but these areas over here, they are very heavily affected by the storm. These are actual parts of the city which have been flooded in the aftermath of this cyclone. So this way, it's possible to create maps of flooded areas. And of course, flooding is highly related to elevation. So you will always want to compare your flooded area map with your elevation map. Copernicus Data Space Ecosystem has elevation data. This is part of our normal data portfolio. We have 30-meter and 90-meter global elevation models, and also 10-meter elevation rasters in CCM, but those are only available for downloading. So now I've changed the way the compare works. It's not a split compare, it's an opacity compare. So I am making the top layer transparent, and you can see the elevation below. So the low areas are white, the high areas are red. And obviously you see that this part of the city, oh no. Yes, okay, login is taken care of. So this part of the city is sort of low-lying. And so this is going to be flooded when the storm hits the town. Why are we using Sentinel-1 for this? Why not Sentinel-2? I can show you another example. This is a place in Germany. which was affected by a large-scale flood, a rainstorm. It's actually called Wittlich. So here there was a record rainfall event, and Sentinel-2 was unavailable for flood mapping because of clouds. So we are looking at the 15th of July. We see the flood over here, right? So the dark blue areas here are the ones that are flooded. And the Sentinel-2 image from the 16th, from the nearest date, is completely cloudy. You don't see anything at all. This image is not useful for rescuing or for urban planning or anything. But this image here shows you the difference compared to the normal situation, right? You can see that the river is flowing in most of its historic floodplain. It's also flowing through the industrial area south of the town. So this shows you the risk and the affected areas. This is something that first responders can directly use. But there are also some areas which look like floods, or at least they are sort of similarly dark, but they are not necessarily affected. This can be evaluated based on elevation, right? So it's also possible to create a 3D view. Let me show you how this works. I go back to the normal view here. I select the 15th, and then I just click 3D over here. And it's going to take me to a different style of window. And I can view the scene in 3D and rotate it around using my mouse controls. And I can also apply a terrain scaling to make it easier to see where the areas are affected. So obviously the lowland areas in the valley are affected by the flood. Anything on a hill slope, which looks dark, is probably not a flood. It could be a tarmac area or some other area, which is generating a low radar signal. So again, we've been through this, the cyclone, the 3D view. So Sentinel-1 synthetic aperture radar provides information about inundation, about flooding. It is not influenced by clouds or by light. Sometimes it's difficult to interpret within city areas because the houses, they produce a very strong signal, and it's not so easy to separate them, but often this is the first source of information if a disaster happens. Now let's move on to air pollution. Here our satellite of choice is Sentinel-5P. So how do you look at Sentinel-5P data? Among the data collections, you have to select Sentinel-5P. And then Sentinel-5P is going to have different layers related to different pollutants. Nitrogen dioxide is the most used one, partly because of its strong health effect, and also because it's produced by traffic. It's relatively easy to understand the sources and the patterns. So what you see here, I mean, it's a really wide area, right? So this is the United Kingdom, France, Germany, Hungary, Italy over here. And still the image is grainy. This is the limitation of Sentinel-5P. Its default resolution is 3.5 by 7.5 kilometers. But the data is generated again every day. So it allows you to look at patterns as they happen if clouds are not obscuring your view. So again, this is a compare scene over southern Poland, over Krakow. It's quite a recent image. Actually, it's from yesterday. In this area, the heating, the industrial power stations, and also the traffic creates quite substantial pollution. So how can you actually view this and understand this in an urban mapping context? Again, you have to apply a custom script. So this script here is called the nitrogen dioxide monthly mean script. What it does is it applies a minimum and a maximum to a palette. And then in a small for loop, it runs through the images during the month or during the study time frame, and it calculates the mean value. So this works in the following way. You have to select the start and the end date over here. And then you apply the custom script again by pasting it over here. I'm not waiting for it to process because it takes a while. This is quite a lot of imagery, but I can show you the result directly in this comparison. Whoops. So suddenly you see a lot more because the gaps are filled in. Since clouds move around, they're not at the same place every day. And also because of the overlap of the different orbits, you get a bit of a super resolution effect between these individual pixels. So this approach enables you to really look into smaller scale patterns, such as the collection of pollutants in these valleys, or also larger scale patterns coming across this area. And again, it's possible to compare this with VHR data. I've jumped to a different example, which is considerably less pollutant. Now we are in Naples, in Italy. And here in one layer, I have my Sentinel-5P nitrogen dioxide monthly mean. And in the other layer, I've got the VHR mosaic. So now, even at the level of individual buildings, it's possible to check the long-term exposure to pollution. And of course, I can't leave this topic without showing you the classical example. You're probably aware that Paris has massively changed its public transport or its urban transport strategy. It is prioritizing public transport and bicycles. It's recreating roads and traffic zones. And so what you see here is a before-after comparison. On the left side, you see the NO2 mean values for Paris during 2018. And on the right side, you see the NO2 values for 2025. So this is really a substantial transformative change. This can show you the effect of a large-scale intervention. So again, summing up, you have daily imagery, but relatively low resolution. It's heavily affected by clouds, but monthly compositing helps a lot. In practice, you want to use this for complementing your air quality sensors. You hope you have a couple of meteorology air quality sensors in your town, and you can cross-calibrate with satellite imagery. But you can also evaluate long-term effects of intervention if you have done them at sufficiently large scale, like this model city, Paris. Now I'm moving on to Copernicus land monitoring services on the example of urban heat and on the example of my hometown, Budapest. Again, I'm changing over to the browser. Let's give a second to this to load. So what you see here, again, I'll show you how I access this data set. So under data collections, instead of Sentinel-2, you go to Copernicus land monitoring service. And then here you can select land cover and land use mapping or biogeophysical parameters. Urban heat is a biogeophysical parameter, but just as a start, I want to show you how land cover works. Again, you just click show latest date after you have selected the data set. And here you go, a land cover map is produced. So this map is a result of the integration of hundreds of satellite images. It's calibrated based on ground truth, and it's available across the whole globe as a basic land cover map. You can use this for sustainable development goal reporting, for feeding it to climate models, for whatever. This data set is part of Copernicus land monitoring service, and it's available in Copernicus Browser and also in the data space for cloud processing. So how does this connect to urban heat? Well, Budapest is quite heavily affected by urban heat waves. So we do get warm periods in summer, especially if the wind comes from the Mediterranean region. And I mean, daytime heat is okay, but nighttime heat, when the heat does not go below 25 degrees even during the night, that's considered quite a severe condition. I haven't shown you how to generate a time lapse yet. Let's go back over here. So right here, I'm on the 10th of August, 2025, and I am looking at the land surface temperature image. Now, this data set is collected every hour. So if I constrain the time to a specific period, like the early afternoon, 3 o'clock. Then I get an indication of the temperature during this period. And if I then move on to see what's going on at night, again, I'm constraining the time range here. Then I can see how the temperature changes from the night to the day and back. But it's also possible to create an animation of this. Let me show you how this works. So you click on create time-lapse animation. You select your time frame. I'm going from the 10th to 11th. And instead of 1 image per day, I want 1 image per orbit. And now the server is running and it's querying the imagery from me from 11 o'clock to midnight, 1 o'clock, 2 o'clock, 3, 4, 5, all the way to the morning and to the evening of the next day. I have this animation and I can play it. And then it's showing me how the temperature is changing in Budapest. During the night, you see the center of the city is quite considerably warmer. During the day, this is also present, this effect. And the forested areas in the north, they sort of have a cooling effect on the town. It's possible to download this time series. It's also possible, of course, to view it as a statistical data set. Right? Now here I have created a comparison between what we refer to as sort of normal conditions in July and heat wave conditions. So this is a normal situation during the night. There's some gaps in the data, but you see it's there. And then this is the day. So normally at night, it would go down to 16 to 18 degrees, and during the day, it would go up to 25, 30 in summer. And now let me show you what happens during the heat wave. During the day, of course, it's super hot. But also during the night, it barely cools down. So these effects can be visualized directly on top of your map using temperature data from Copernicus Land Monitoring Service. Now, the problem with this, of course, is that it's low resolution. So you can see, of course, the effect. You can check what's going on day by day, but it's difficult to compare this with the actual land cover or with the processes that are going on in the city. But we also have another data source. Copernicus Sentinel-3 has a thermal sensor. So this is the level of detail that the Sentinel-3 thermal sensor is going to give you. It provides imagery with a resolution of 1 kilometer. And so you can overlay that, and then you can see which sort of district of the town is hotter and which is colder. And then additionally, you also have Landsat. This is a recent addition actually since the beginning of this year. And Landsat has a thermal sensor as well, and that has a resolution of 100 meters. So with 100 meters resolution, you can really look into heat islands or individual hot and cold spots in the city. And this even has sufficient resolution to be compared directly with individual buildings or individual changes in your town. This is the land surface temperature custom script for Landsat. Again, you apply it as I showed, you copy the script, and then you paste it into the custom script window over here. It's also possible to load the script directly with a URL, and that supports the sharing links. So let me show you the actual case study here. Oh, I'm already showing you the result. So this is where we start. This is a sports area, a sports ground close to a railway station in southwestern Budapest. There used to be a football field in the middle with this sort of running track and relatively large areas of green space around this sports ground. And then, I mean, Hungary is very strongly into sports. It's a very strongly supported thing, which is actually not bad. This area was reconstructed. So the athletics area was reshaped. You see that the red rubber surface covering is covering a lot larger area now. And also this additional football field was added, and that's not a grass field, but that's a so-called astroturf field. So it has this plastic covering this artificial grass. Right, so before, after, before, after. Now we can actually ask how this has influenced the local temperature. How does this influence local climate when we have a heat wave? So this is the situation before, and a Landsat thermal image from 2021. It's scaled. Actually, I can remove the VHR. Right, so this is the situation in 2021. This park, of course, is a relatively cold spot, and the sports ground itself is sort of medium warm compared to then the office buildings over here. And now we have rebuilt it, it's renovated, and this is the effect. So you see that this is a massive local hotspot because the plastic surface heats up very strongly during summer. So we did have a strong intervention, of course, for local sports, but it's also creating a thermal island within the city. And with Landsat thermal imagery, it's possible to actually visualize processes at this scale. Well, where's the catch? The problem is that Landsat thermal data is only available once every 10 to 12 days. So if you want to look at the effect of something like this, you have to find an image which overlaps with the weather conditions that you're interested in, because it's not going to be available every day like Sentinel-3. So Sentinel-3 is available every day. So again, you can create time-lapse animations that show you the thermal conditions at an hourly rate from Copernicus land monitoring service data. You can look at slightly higher resolution thermal imagery every day using Sentinel-3. And you have high spatial resolution heat mapping from Landsat. And this is even sufficient to show you the change from a local cold spot to a local hotspot due to a renovation project. So if you want to investigate your urban heat islands, you can combine these data sets. You can look at different steps in resolution, and put together, you will be able to see the effects of various interventions. So much for case studies. I want to show you now how to share your data, how to share your data products in Copernicus Data Space ecosystem. I'm going back to my browser again. So this is the ecosystem main page. And here under Analysis, you have Sentinel Hub dashboard. So if you go over here, you see a lot of information related to your user account, like how many processing units you have consumed, what data collections you have, what your user settings are. And here you can go to what's called the configuration utility. Now, a configuration is a unique combination of a satellite data set and a visualization script. And if you create a configuration, it's possible to share it in several different ways. So here, I have a configuration I generated specifically for this webinar. I have quite a lot. Yes, SPACE4Cities. And so this goes, I click new configuration, and then in this configuration, I can add individual layers. No, Sentinel-2 NDVI, obviously. Right, so here my data source, I can set it as Sentinel-2. And my data processing, I can select it directly from the this list or from the custom script editor. So here I'm using NDVI copy script to editor. I'm setting the script. I'm saving it. And so now I have an extra layer. And if I want to share this with somebody, I can take this service endpoint. And for example, I can generate a WMS. And here's my WMS URL that I can copy. And that can be directly added to a WebGIS or directly added to desktop software. This is unique to me. So if somebody is using it, they're actually using my processing quota. But in their WMS service, they will have these two layers with these two visualizations. So this is the first step towards creating a WebGIS or projecting satellite data into your urban mapping solution. Now, once more, I want to show you how to access CLMS datasets and the processing quota on the cloud. So when you register, or if you go to your profile, or I can go to my profile like this, it's going to include my personal information. And then here, you have to select what kind of user you are. I'm from an SME, but you are probably from a national, regional, local public authority. And again, for purpose of use, you can select public sector. And here, if you click, I'm also interested in accessing Copernicus contributing missions data, you have to accept a specific license, and you have to select your user category. Again, you will here be able to select public agencies or public services, and that will be the first step towards accessing the CLMS dataset. This is just a short overview of the quota. It's different for individual APIs, but all in all, it's going to be sufficient even to do national or regional level data processing at the scale of hundreds of square kilometers. If you run out of download quota or processing units, you can buy more. So it's possible to go through our cloud provider CrowdIS and directly buy more quota for Copernicus Data Space Ecosystem. You can also make use of sponsorship opportunities like ESA Network of Resources, or you can look into these account type changes for Copernicus services. CCM user categories. This is what I wanted to show you. Yes. So national public authorities, union research projects, Copernicus services, and international users, international organizations, and the public. And this is the list of the individual Copernicus contributing mission datasets, such as the VHR mosaics, the Urban Atlas, the 2024 mosaics, and so on. And D means download access, and V means view access. So if you're just a member of the public, you can view the data, but you can't download it. If you are a public agency, then you can download the data, or you can also process it in the cloud. This is just an overview of the upcoming developments in Copernicus Data Space Ecosystem. Actually, I can flick forward to these. So we are going to get more high-resolution Copernicus land monitoring service data very soon. And this includes water, snow, and ice coverage, but also high-resolution vegetation and land cover, layers for bare soil, open surfaces, grasslands, wetlands, small woody features in the landscape. So this is also something that you can integrate in your processing chain. We are going to have more capabilities for cloud processing with new releases for OpenEO. We also plan to integrate Stack and OpenEO directly into the browser. And we are looking forward to the arrival of new space data for Copernicus contributing missions. This will include hyperspectral and high-resolution thermal data. So all in all, Copernicus Data Space Ecosystem is a tool that enables operational services. It's not just for exploring data. It's not just for prototyping or debugging. It's a very powerful backend processing service, which enables you to build a service that runs straight on the user's system and on the cloud. We have near real-time data, which means you can use that for safety or monitoring, and it supports integration with handheld GIS systems or desktop. Copernicus Data Space Ecosystem is also a collaboration platform, right? I mean, what is a good collaboration platform? It's a place where a lot of people are there. It's a place where many different tools can be used, and it has to be free and open. So CDSE is publicly owned. It's governed by the European Union institutions. It's open to everybody. It's very widely adopted right now. We have 550,000 registered users, and it's growing strong every day. It has open standards such as OpenEO and also Sentinel Hub custom scripting. So it allows you to share tools that you have created or to use the results of other people directly in your processing system. It's very flexible from small-scale browsing to large-scale global service development. And it facilitates the path from an experimental tool to an operational service through these individual steps. I think that Copernicus data space ecosystem is transformative for the Earth observation sector. It's a real game changer. It's really making it easy and cheap to access Earth observation data. You don't have to invest in a big data processing solution to create something. Your bandwidth or your processing capacity is not limiting what you can do. And learning the technology is a series of incremental steps instead of a steep learning curve. Now, before we move to the Q&A, I just want to quickly flick through sources of additional information. So of course, we have a documentation page where the tools are clearly explained. We also have a community forum, and don't hesitate to ask a question or to share a result, because this is a really, really active forum. We have users answering users, but we also have our own experts monitoring the forum and answering your questions. We have a YouTube channel where we are posting regularly technical videos and case studies, explanations of new capacities, new tools. So this is an easy way to follow. And of course, we have online webinars like this one here. Thank you so much for following me through, and I am here for your questions.
Okay, brilliant. So thanks, obviously, for this great presentation. It was perfectly timed, 1 hour. Amazing. I don't know how you managed to keep track of it so well, but I think obviously a lot of content and ground covered, but and also obviously a lot of people posting questions, which we'll tackle now. But yeah, first of all, really thanks again for this well-rehearsed and well-prepared presentation, András. So I think a small note, I have to unfortunately apologize that while you were speaking, I was posting links, but I realized that I was posting the links into some private chat window that someone opened towards me rather than the main chat, but I caught up on it. So apologies to the others, but we will obviously share all the sort of presentations with the links together afterwards, so you can have the time to follow up the examples that you shared and link through. Okay. Before I open up those questions, just a small clarification. That was a question by me. Sorry, I'm monopolizing this maybe, but you showed obviously for cities and regions the level of access to, for instance, the contributing missions data as an example. Is this data just for the cities themselves, or can they also share this data with partners, for instance, companies that are processing it, they're working with together?
You can actually share it with your subcontractors. If you look at the terms and conditions and the license agreement, it states that this is also for for-profit institutions, for companies who are delivering services in the framework of a contract with a public institution.
Okay, great. It's great news, I think. Excellent. Okay, so I'll try to now scroll through the list of the different questions, and we can maybe take it one by one. Many more popping up, but I think obviously I'm maybe prioritizing those that have been liked much more. I think one of the biggest sort of like questions is like when you talked about the CDSE cloud and the services, the question was, who owns the cloud?
The European Commission and ESA. So this is part of Copernicus program. Copernicus program is delivered by ESA and the European Commission. So this is completely publicly owned. It also has a governance structure where these partners have a say in the individual changes. It's built by a consortium of industrial companies, but the ownership is completely public.
Perfect. Perfect. Thanks. Then I think the next biggest question was, can you measure, for instance, carbon sinks of specific areas?
Well, not directly, because I mean, measuring carbon dioxide process in the air is quite complex. But through vegetation biomass and vegetation vigor, you can do this. And there's also actually a data set, leaf area index is directly available as part of Copernicus contributing missions, Copernicus Land Monitoring Service. And so that is very closely related, of course, to carbon fixation.
Cool.
Vegetation properties, leaf area index. So this, for those who are not biologists, leaf area index relates to the actual surface of leaves above a unit area of ground. So for 1 square meter of ground, how many square meters of leaves do you have? And this is, of course, closely related to the activity of carbon sinks. But carbon processes also relate to soil properties, to below ground activity. So this is a bit complex, but a lot of carbon monitoring is actually done directly by satellite. And of course, vegetation vigor and vegetation growth are the main parameters behind this.
Okay, excellent. Then another question was, highly voted, was like, is there a manual explaining how to use all this advanced functionality of Copernicus Browser? So
yes, of course. So in our documentation, API, Sentinel Hub, user guides, beginner's guide, there is a guide to the API, and there is also a guide to Copernicus Browser over here. But I actually think that the easiest way in is through a YouTube webinar. We actually gave a webinar about advanced use of Copernicus data space ecosystem a while ago. Here, advanced use of Copernicus Browser. So it's here I can, oh, sorry. What the hell is going on with my ads? Sorry. Anyway, it's available in the YouTube channel, and I can also post the link in the chat.
Excellent. Yeah, you're lucky with the ad. All right.
Yeah, my other browser has an ad blocker, but that's a bit slower with Copernicus Browser.
But it's normal with YouTube, yeah, so don't worry.
Yeah.
Then another question was, could you explain how this data generally can be legally used for commercial projects? And what do you need to in terms of, I guess, actions to make it commercially usable, right, or something like this? I think that's all.
Well, regular Sentinel data and Copernicus land monitoring service data can be used for any purpose, including commercial purposes, completely for free. So that's the easy part. For Copernicus contributing missions specifically, I think you have to talk to the data providers. So there you would have to submit a regular price quote request, and that would give you commercial access to the data. It's possible to do this again through the CrowdIS, which is the commercial cloud provider linked to CDSE, and they have a data marketplace. I think this should be okay.
Which doesn't look safe.
I don't know what's wrong here. So they have a data marketplace also for commercial data providers, and that enables you to have relatively straightforward access also to the data sources, which are also used for Copernicus contributing missions.
Brilliant, brilliant. But I guess as you explained earlier, like if you're a city or a region, you can get access to this data, at least the ones available on the portal for free, and you can also use it with your partners, which if they are subcontractors of you, right? So
yes,
this means even like that means a commercial entity might still be able to use it commercially as part of the subcontract, I guess, the city.
Yes, yes.
Yeah, that's very good. Then also a question about maybe more specific around tools. So is it possible to link the data sets with Cesium?
Cesium, I don't know what Cesium is, unfortunately.
Yeah, I'm also not very...
I would have to Google that.
Yeah.
It's possible to create an API request and then outsource the data directly to a processing platform or a tool within this request instead of downloading it and pushing it to that platform. So I guess that should work, but unfortunately, I don't know what Cesium is. Maybe who asked the question can quickly clarify.
I'm not sure if they're still... I think 3 other people voted this. So anyone wants to clarify what Cesium is? It's a 3D platform. Okay. So yeah.
Well, if it accepts data through an API, then it works. It should be possible because I know other 3D platforms like the Swiss Topo platform works directly with Sentinel images from a configuration. So you go the same way. Actually, you create a config, and then you provide the service endpoint to the platform, and then it should probably be able to drape the satellite imagery, like the most recent satellite imagery, on the top of a 3D image.
Okay, cool. There was another question. I mean, now I've got just maybe single vote questions. I'll take a few examples here because we have a bit of time. Which data would you recommend for heat hotspot analysis or more advanced for city climate analysis?
Well, if it's done at the local scale, at the small scale, then probably Landsat. So I would try and find a time based on meteorological records where there was like a heat wave or something. Actually, AI is super good now at analyzing meteorological records. Just when preparing this, I prompted when was the last major heat wave in Budapest, and it gave me a comprehensive list. So you select a very hot time, and then you try and find a Landsat image that corresponds to that, and then go through the land surface temperature custom script. Again, if you don't have Landsat, yes, so here's the script. It's actually rather nice because it's physically based. It does a small land surface classification because different surfaces have different emissivity, and then it uses that to calibrate the radiance temperature that the sensor is experiencing. So you can use this. If Landsat is not available because you don't have it on a specific date, then you can go through Sentinel-3. I can show you the Sentinel script as well. It has quite a detailed manual explaining how to set it up and how to use it. It's a Fusion script, so it's not quite trivial because you're using two different data sources here, but it works.
Cool. Yeah, great. So then a few more maybe. One around is like, can we also look at Ukraine, or are the maps hidden due to war?
No, it's not hidden. CCM datasets don't cover Ukraine. The CCM datasets only cover the European Union. So the very high resolution data is only there. But all the other data, the CLMS datasets and the regular Sentinel data, they cover all the globe.
Perfect. Then some others. How can images of different satellites be overlapped?
Well, using compare mode again. So you can do this over here. Here's my, oh, this is cloudy. Here's my image of Budapest. It's a true color image. I want to compare this with a Sentinel-1 mosaic. Then here I click add to compare. And then I open another data source, Sentinel-1 mosaic. I add that to the compare as well. And then here I have them one over the other. But if you want to do like an API level process, or you want to process something on the cloud, then you can go through a Data Fusion custom script. So there you would have to select here we go, custom script, use additional data sets. And then here it gives you the list of all the available additional data sets that you can use. So for example, here you could integrate radar data with Sentinel-2, and then you would have to have a script which handles this properly, but it's possible to actually handle these two data sets together.
Oh, I'm just amazed about the fluency that you have with the tools there. So well then.
So this little picture here is actually, it's a Sentinel-2 mosaic, but it's converted to grayscale. And the blue parts are from Sentinel-1, the flood data, which is overlaid with a small classification. So this is an actual Fusion script. It's not a compare, but the script is calculating these two things together and outputting one single output.
Perfect. Yeah, another thing, maybe just, so there's someone who works for a public organization, I guess, which is not a region or a city, but if they want to register, can they use a public profile to do so? Select public in the profile, or what would they use?
I think so. I mean, if you are in doubt, then you just have to submit a support request. So here, under submit a request, you can always ask more detailed questions like this about specific use cases or changing your user profile to a different type of account or something. So it's also possible after you've registered, if you haven't set it up right now, you can submit a request to change it.
Okay.
Note, if you work in a public organization, the profile is not public, it's public organization. Where can I show this?
Yeah. Yeah, you're right, because public is anyone, right?
Public is general public, but
Yeah.
over here it's national, regional, local public authorities, right?
Yeah.
Or if it's an NGO, then you say NGO.
Okay. I think that should clarify it. And I guess if you misclassify, you'll anyway have maybe a verification loop, and that could be rectified as part of this, no? So,
Yes.
yeah, yeah. And then I'm going to go a final one now, because it also has an upvote. So during monsoon or rainy season, most imagery are cloud covered. Are there any alternatives?
Yes, you can go to the mosaics. So in areas which typically have very high cloud cover, I'm going to the Philippines right now. So here again, the latest image is typically extremely cloudy, but the mosaic is quite okay. So as long as there is regularly a period of no cloud cover. I mean, the mountains here are still, you see they have gaps, but most of the lowland areas, they are nicely covered by the mosaic. And if this is still too cloudy, then you have to go to Sentinel-1. Sentinel-1 is not going to be cloudy because it works on a completely different physical principle. You can also make vegetation indices quite similar to NDVI using Sentinel-1, and many different analyses are possible. But of course, it's different. You have to learn how to work with it.
Great. I think we will leave it with this, with the questions. Maybe just also to say there were lots of positive comments in the chat about your talk. I think it was very much appreciated by everyone. So well done again, András. And obviously, there were some questions about whether we share it. Yes, we are obviously recording this. And we will, I think, András, you will send me your slides eventually, right? Maybe today or tomorrow.
Yes.
And then we will also share this as a PDF on next week on our website, plus the links that you also provided as examples. Yeah. So great. I would then maybe just take the moment again to sort of like give you a little applause. Thanks again for really a very interesting and insightful and exciting or entertaining webinar. Yeah, you can see a lot of claps as well coming from the audience. It's great. Thanks for your time, the effort that you put into preparing this, and the professionalism. I hope that also our audience found this very useful and are getting inspired to do more things. I understand, obviously, there was a lot of content covered, and maybe it was tricky to do the same thing now with the links while you were presenting and sharing. But obviously, you have now all the basics, I hope, as an audience to then replicate some of the examples that András shared with you later online, watching the video, pause it, and then use the links to kind of see and get your first experience. Okay, so with that, I wanted to obviously thank you all as well, the audience, for joining and showing your interest in also our project, SPACE4Cities. Please continue following us. There will be new things coming along the way. We will also organize more webinars later, as we have, for instance, sharing what our different companies that we're working with are producing. So there will be some deep dive tutorials with their tooling as well coming up, and there will be the replicator call again for other citizen regions to then join in and adapt some of those solutions that we will select. Stay tuned. And I wish you a great rest of the the week and rest of the day. And yeah, hope to see you at another event like a webinar soon. Okay. Thank you all.
Thank you very much. Thank you.
Thanks.